Welcome to my presentation. Today I'll be talking about some of the exploitation techniques that can be found in the medical devices that use PKCS11 and OPT architecture. Let's get started. Who am I? I'm a senior product security engineer at Beckton Dickinson Advanced Patient Monitoring. I have masters in cybersecurity from UNC, USA. Right now I'm focusing on secure by design principles to make sure security is not an afterthought, but foundational element in how we build systems. I'm especially focused on secure by design principles into development of high-stake technologies like medical devices that directly impact patient safety. I used to be a Synax red teamer, so an old habits die hard, so that's why I still do red teaming. I still do bug bounty and CV hunting as well to keep my offensive side alive, which is important for secure design as well. I've started writing blogs. Recent ones are about OPT, secure architecture, etc. I'm just getting better at it, so they might not be good, so read at your own risk. All right, agenda. I'll start with why medical device security matters. Then I'll give you introduction on zone, T overview, OPT, how PKCS11 fits into this overall device architecture. Basically, I'll be giving introduction on these, which is going to make it easier for you to follow the exploitation techniques that will be followed after these. I'll also touch on detection and monitoring strategies and what we can do about these kind of attacks. I'll also give you overview on secure storage implementation strategies and misconfigurations that are commonly found in this kind of implementation. I'll finally wrap up the presentation with talking about challenges in enforcing strong security controls in medical devices. All right, there's a fact for you. More than 60% of connected medical devices in hospitals have known vulnerabilities, according to CISA. It's not a small number. It means majority of the device in the hospitals have vulnerabilities. Having said that, why medical device security matters? If the device that's connected to patient is compromised, for example, if attacker could compromise the patient monitor and change the value displayed on the screen, uh, the consequences isn't just data loss. It's much more than that. It could directly lead to incorrect treatment or delay in treatment, sometimes even death. Let's look at a real case here. In 2017, there was this pacemaker that were implemented in almost 500,000 people. So there was this vulnerability that allowed an attacker to change the heart pace remotely. So they could even run the battery right by successfully exploiting these vulnerabilities. So the exact details of this vulnerability were not disclosed, but the fix was eventually released. But that wasn't even a main problem. So the real challenge started after that. Since this device is implantable, so it required invasive surgery to get the device out and update the firmware. Um, some people couldn't even have survived. So even applying a fix is not as straightforward. So if the device had a capability to update the software remotely, then we need to make sure like we have like solid security controls to open up that attack surface, like the capability of updating the software remotely. So it's not just technical challenge, it demands a 360-degree view across regulatory, operational, and human impact. Let's look at how medical devices are classified, commonly classified based on their invasiveness and the based on invasiveness. So it could be non-invasive device like a finger cuff, or it could be minimally invasive like endoscopic or catheter that goes into your body via minor incision or a cut, or it could be invasive devices. The perfect example for that would be implantable or pacemaker, etc. So we have a few classes, so invasiveness is a key factor in determining this risk profile of these devices. Based on the risk profile, they have to have different kind of security controls. They go through different kind of scrutiny by the regulatory bodies like US, by FDA, which is in US. In EU, we have such regulatory body, which is MDR. So like we have different classes in US, like class 1 being low risk, class 3 being high risk. So these invasiveness is a key factor in determining the risk profile of the device. So let's talk about something what most people overlook, platform and hardware security. So these devices are going to be deployed in what we call uncontrolled or hostile environment. It means anybody could walk up to your device, try to tamper with it, try to clone the software. For example, if the interface, like a hardware external interface, are exposed or they don't have proper protections, attacker could try to access that, modify the boot parameters to boot into a Linux with the root privileges. So at that point, all the security controls you have on the software, like authentication, etc., will be easily bypassed. So that's why we need to have solid hardware security measures and platform security measures to make sure these attacks are not happening. So one of the countermeasure would be to have TPM or TEE, which provides root of trust for your cryptographic keys or any other sensitive data. It also enables you to have secure boot. Basically, you are making sure you are loading only trusted modules and firmwares once the device boots. So that's what secure boot provides. It also TPM or TE also enables you to have full disk encryption that protects against offline attacks. It also you can also have like anti-clone, anti-tamper properties to protect against these kind of attacks. Okay, trusted execution environment. So it's a secure area within main processor. So it's within host processor. It's a dedicated area and it's built right into the CPU. It's a hardware-backed security mechanism. That's why it's very cost-effective alternative to physical edges because uh, it comes with the hardware. So if you buy ARM processor, it comes with the processor. One of the well-known implementation is ARM Trust Zone. It's a security feature provided by the ARM processor. Starting from V7, it got fully adapted. It's a hardware-backed security mechanism. How it works? It literally splits the processor into two different worlds, secure world and non-secure world. It means code in the secure world code in the non-secure world cannot access secure world. If they want to access, they have to go through proper set of standard and defined APIs called global platform APIs. Um, you can also have like secure memory and secure peripherals. You need trusted OS, of course, to make it functional. So TE specification doesn't talk about storage. It just provides runtime, like for your application to run securely. But you can attach some kind of storage medium to the secure side of the processor. So that's how you achieve secure peripherals or secure storage. That's what manufacturers and vendors do these days. And there is another component that we need to talk about is trusted firmware. It's a software implementation. It's a low-level implementation that sits one level above the hardware. It provides the secure monitor call. It's basically a CPU instruction which is going to signal the processor and say, "Hey, this is the time to switch mode." This is think of it like a switch that switches the mode from secure world to non-secure world. It acts as a gateway, and this trusted firmware is part of ARM processor firmware implementation. And it's not just ARM, even Intel as TXT and AMD as SPM. At the end, all of them provide the same thing, trusted execution environment. Okay, let's look at some of common use cases for this. The first primary use case is to store cryptographic keys securely, the secure key storage. So you can store like keys for secure boot and keys for encryption securely in this secure storage. And you can also perform cryptographic operations securely. So it supports all major crypto primitives and also it will support all crypto algorithms. So for example, if your application is talking to any other application via network, so and as part of TLS communication, if it's doing the certificate verification or decryption of the packet, so your application doesn't need to know the key. So you can literally decouple that verification part to TE. That way, even if your application is compromised, your key is not compromised. Your key is safe in the TE. So your application call that specific function in the TEE, in the application that runs on TEE, and have the data decrypted and send that back. So this way you are decoupling that sensitive piece and have that run in the secure side of the processor. Um, you can also use this as a general purpose storage medium where you can store like PHA or any other sensitive data. So you can also secure your AML models that's used to like predict some kind of output like cancer or any operations. So you can also secure those models from being reverse engineered. You can save those models and securely run these models in TE, but you also need to make sure like it has got enough memory so to make sure the performance is not taking the hit. It also can um, provide secure biometric processing if your device has one. And TUS. So we talked about hardware, but you need some kind of software to take advantage of that. So in order to make it functional, you need some kind of software that runs on above trusted format layer uh, in order for us to make use of it. So that's where TEOS comes into the picture. So this is very tiny OS with smaller code base. That's intentional because smaller code base means less attack surface, easily predictable, and less vulnerability. Also fewer bugs. So it's got greater flexibility than TPM. So TPM is carefully scoped to meet TCG specification, but TE is not like that. See, TE is flexible, so it's up to manufacturers um, to implement TE however they want. So you can even implement all TPM security features in TE. So that's why it provides greater flexibility. And there are common other type of TUIs that exist in the market. Opti, it's open source, Trusty by Google. That's what's running in Android. If you're using Android phone, there are high chances your phone uses Trusty. And QC by Qualcomm and SafeOS by Apple. So next time when you pay at the terminal or you unlock your phone using Face ID, there is a TUOS that's silently guarding all your secrets behind the screen. So Opti is a type of TEOS. It's open source. It runs alongside a rich OS. As you can see in this diagram, so on the left hand side, you have your rich OS Linux operating system. On the right hand side, you have Opti. So whatever you see in the green blocks are your custom applications. You design your custom application based on your product use case, and they have to talk to each other via these APIs. I'll talk about that in a bit in the next slide. They are called global platform APIs. So as you can see on the right side, these trusted application are isolated between each other. Um, Even if they need to talk to each other, they have to go through these APIs. They are secure APIs. And for example, if you have some kind of PHA records stored on the RichOS Linux side, they can stay encrypted. And if your application wants to get them decrypted, it can send that to your trusted application. Then your trusted application will have access to the keys. They can access the hardware resources and fetch the key, and they can use that to decrypt the PHA records and send that back to your application on the Linux side. So this way your application on the Linux side doesn't need to know the key. So you are decoupling the sensitive piece and you are separating the use case and you are having that handed over to Opti. So that's how you achieve security. Even if your main application compromised, even if your entire Linux is compromised, your key is not extracted. It cannot be extracted and your key is secure. As you can see, the SMC call is the one that switches the mode that acts as a gateway between two worlds and global platform APIs. So in order to enable secure and interoperable communication between your application on the Linux side and the trusted execution environment, global platform has defined standardized set of APIs. These APIs act as a contract, making it easier for developers to write secure apps without worrying about vendor-specific implementation. So while being abstracted from the hardware-specific details of the TEE, this way your trusted application doesn't need to the hardware resources, internal logic, or it can just follow what's in the global platform. It can just call those global platform core APIs to do the needful. Uh, for example, there are a lot of different type of T is specific implementation, like OPT, QC, trustee. So developers don't need to know the any difference between them. They can just call these set of APIs. So to be specific, there are two set of APIs. The first one is called the client APIs. This is what's used by your application on the Linux side to talk to the trust application. So they are responsible for setting up the session, initializing buffer, setting up shared buffer, etc. And the core APIs, this is very important API. This is used by your trust application to access the hardware and the secure resource. So for example, generate key commands, like a transient object. So you can generate keys, fetch the keys, generate random numbers. So these are the core APIs. So introduction to PKCS11. Think of PKCS11 as a universal translator between your application and the secure crypto device. So it's a way to work with the crypto devices, for example, HSM physical devices that contains cryptographic objects like keys or certificates. So it's a way to work with those hardware specific device. Again, it's another layer of abstraction. This way, like you don't need to know about these different HSMs. You can just have PKCS libraries implemented on your front end or your software. Then you can issue PKCS11 commands to the HSMs. It's HSM manufacturer's responsibility to convert that command into device specific commands. So it's implemented in the firmware. So it creates another layer of abstraction. It's a universal language between your application and the HSM. So it uses object-based approach. As you can see, like all these data that you store in these HSMs are just objects in front of PKCS11 eyes. That's how it achieves the technology independence. So there are a lot of objects, key objects, certificate objects, data objects. This is general objects. It could be any data, any blob data like PHA, or it could be anything, or secret key objects. So the libraries are available in common programming language like C, Java, Python. So you can implement that in your programming language, and you can just issue a set of PKCS11 commands. And the manufacturer must have implemented PKC11 libraries that convert those commands into the device specific uh, commands, codes. So quick recap. So far we have seen TE. It's a concept. It's a trusted execution environment. It provides secure running environment for application to run securely. Trust Zone, it's a security feature provided by the ARM processor. Opti is a type of TOS, sits on top of Trust Zone. It's a OS, and that's Opti plus Trust Zone is what provides TE. And global platform APIs, they are a set of APIs defined by global platform to uh, enable the communication between your application on the Linux side to the trusted application. And PKCS11, it's a universal language to talk to the secure element like HSM or TE, etc. Here, so in this architecture, usually I have as I've said earlier, PKCS11 usually will be implemented in the HSM devices, actual physical devices. But here in this architecture, this PKCS11 will be implemented as a trusted application itself. So what it will do, as you can see on the left side block, you see OpenSSH. It's just a command line utility that's commonly found in the Linux, and you also have like PKCS11 tools. So they both of them are command line utility. So you can call those commands, and you can issue PKCS11 commands that will in turn call libcktac, which is a library that implements global platform internal APIs, then which is responsible for calling the driver, such as the mode using SMC instruction, then it reaches OptiCore, then OptiCore will redirect the traffic to the corresponding trust application. Then here is where your PKCS11 commands gets unwrapped, and your trust application will do the one-on-one mapping between the commands you issued versus the corresponding internal core API commands. Then again, it calls a couple of libraries, and it finally reaches the file system. So you don't need to worry even if it stores sensitive data in the Linux file system. So by the moment it leaves Opti, they are encrypted. So even if they use Linux file system to store the sensitive elements, They are encrypted, also have integrity protection. So this is one of the secure storage implementation strategy. I'll cover this later in this slide. Okay, authentication in PKCS11. So this TA also has authentication because it needs to authenticate those calls, authenticate the application that's making the call to the TA. That way it needs to make sure like it's the right caller. Uh, here, as you can see, so there are three slots, like slot 0, slot 1, slot 2. They are so if you are using physical HSM, so each slot would be um, referred to each physical HSM. So, but in this case, we are not using physical, so it's virtual emulated HSM. So this TA will create emulated HSM, basically logical HSM. So from your application side, it doesn't know like these HSMs, it's just virtual. So that's why you are able to see all these slots, slot 0, slot 1, slot 2. It all virtual. As per default design, these slot authentication are defined at the user level. For example, if you have like two, three applications running under the same user, all these applications will have access to these particular slots. Also, the objects that's stored inside the slots. So you need to be very careful while making such designs because you will never know like what are the applications that will have access to your sensitive objects. If you look at the authentication type to get into each slot, so there are two types by default. So pin based, it means it's just numbers that's used by your application. So this number needs to be supplied to the trust application. Then they will check these numbers. Then it will let the application call in. So that's what's called user pin. And there is another set of pin called security officer pin. This is basically administrator user that's responsible for like changing user pins, etc. Both of these pins should be saved and stored securely. The second type of authentication is identity-based authentication, where you map a Linux user ID to the slots. It means when you make the call in the runtime, it will convert your Linux user ID. It will use your Linux UID and make sure it's the right UID, and it will allow the user. That's identity-based authentication. And other important thing to note here is object access policies. So these object access policies define what operation you can do on the objects that you store inside these slots. They are defined by access control flags. So there are a lot of flags, for example, CK exportable, CK sensitive, CK always authenticate. So these are the flags, the example flags. If exportable, if you set exportable for a particular key object, you can export those keys. So you need to carefully define those access policies. If you don't properly configure that, it can lead to catastrophic incidents. All right, so this is what it will look like if you use PKCS11 tool. So here I use PKCS11 tool. I import that module libckTEC, which converts PKCS11 commands to corresponding global platform set of APIs. Then I'm querying the slot index 0 type data. So it's I'm reading the object, so I specify that using a flag, and I specify a label of the data object and extracting, so it just output file name. So as you can see, I'm able to extract the data from that. So this is what you can do if you have these tools available. You can even use OpenSSH, so OpenSSL in this case. On the second diagram, you can see this is what it will look like if you list those objects. So you can see it's a private key object, so it's got a flag extractable, so that's not good. But some formats won't allow you to extract the private key if it's marked as private key, and even if it's marked as extractable. So it won't allow you to do that if it's private key object. As you can see, data object, so it's got flag modifiable. Again, it's not good. Even if it doesn't have extractable, you can still extract data objects. So that's by default. So well, you need to carefully design these flags. You need to make sure they are configured properly. As you can see, I'm entering the pin like on. If you look at the fourth line in the first diagram, I'm entering the user pin. So I just you can brute force, or you can. I'll talk about that in a bit about the pin misconfiguration. So once you enter the pin, that's it. You are in. All right, let's look at other common weakness. Um, so the main weakness is the weak or insecure pin management. So sometimes uh, application just use like known or easy pins or default pins that come with the firmware, and sometimes these pins can be stored on the flat file system because your application needs to have access to these pins to talk to the slots, right? So if it's stored improperly, so if it doesn't have proper ACL hardening on that file, then like any application or even unauthenticated user can access this pin and access the object that's in the slot. So you need to make sure you have proper ACL hardening on the file that saves this pin on the Linux side. Sometimes the TA doesn't have brute force protection, so it means you can just write a script to do the brute force on like at specific interval, and you can find your way in. And sometimes the application just hard codes the pin in the source code, and source code can be publicly available, or the application doesn't have proper abstraction, sorry, a proper obfuscation. Um, then the pin is compromised. And the other common weakness is broad privileges or privilege sprawl. So over the time, you will add more application under the same user, and you lose track of it, and that leads to privilege sprawl. So applications that are not supposed to access or that are not supposed to have access to the slots will have access because you are adding these application under the scope of one user. And other important misconfiguration is object control flag. So if you don't properly set these flags, then it leads to catastrophic incidents because these flags define what operation you can do on specific object. All right, detection and monitoring. So just because Opti doesn't have like rich interfaces like Linux, does like it lacks like rich way to work with, doesn't mean you have to leave it unmonitored. You can still monitor the trust application. So there is a concept called pseudo trust application. It will think of it like a privileged container. So it has same privilege as Opti core because it's built right into the Opti kernel. So it has more privileges. So you can set a baseline. You can basically set a baseline on like what operations your trust application is performing, like what are the commands that it typically needs to issue. For example, the read object data, like write object data. So is it supposed to read or write particular object? So you set a baseline, then you enforce a policy, you track these function calls, then you can have this sudo TA report back to your application on the Linux, where you set up a full-blown monitoring system. You can even send a log outside to your backend for analysis. So this is how you should be used, but there is no no default sudo TA provided, but you can build one. So the communication from sudo TA to your application on the Linux side is happening via the supplicant. It's a separate component. I'll talk about that in a bit. Hi. So I have made this tool called OptiPKCS11 security audit tool. So it's going to perform whatever I have just described. So it's going to automate the entire attack scenario. There are a lot of cool features. It can do brute force for you for the known weak pins. It will also enumerate the objects if the authentication is successful. It also assess the object access control flags to see if they are properly configured. If not, it will extract the data object or any other sensitive objects out of the token or out of the OT. It will also scan for sensitive log files like tec.log in the Intel Linux system wherever it has access to see if it can find any sensitive information like pin or any other sensitive information related to this OPT or related to this trust application. All right, let's look at secure storage implementation strategy. So this is implement. So if your device has OPT, then secure storage must be implemented according to global platform specification. So this secure storage can be used as a general purpose storage. You can store your page data or any other sensitive data that guarantees confidentiality, integrity, um, and it typically supports two type of implementation. So the first one, by default, it uses a Linux file system, uh, aka rich execution environment as its storage. So by default, it uses data slash t directory as a secure storage space. So each persistent object is assigned the internal identifier. So this is the identifier which is visible in the Linux file system. If you navigate to data slash te, you'll find like one, two, three lot of file numbers. You'll also find derf.db. It will like contain all the objects that are in secure storage. So these files have proper integrity protection. So even if you try to access the file, open it, you cannot do that. It's just a garbage because they are encrypted. And the second type of implementation strategy is using RPMD, partition of eMMC device. So it's part of eMMC specification, just generally very small in size, but it's not great for storing large amount of data. Maybe you can, so in ideal world, you can use both configurations. So you can use RPMD to store keys or any other small elements while you use rich execution environment to store bulk data like PHA or any other sensitive data. All right, TE supplicant. So the TE supplicant acts as a bridge using your TA trust application in TE can delegate certain operation that it cannot perform directly. For example, if it uses REE, like Linux file system, the TE encrypts the data, but it cannot write to the file system because it doesn't have proper privileges, it doesn't know anything about Linux. It uses TE supplicant to make those input output operations. So even if it uses RPMB as a secure storage, Opti doesn't have any eMMC controller to identify the partition to write to that partition. So it doesn't have that controller because, as I said earlier, Opti OS is very small, tiny OS. It doesn't have those controller or drivers. So it relies on TE supplicant to do that. Think of it like a TE's helper in the normal world. As you can see here, if your trusted application wants to write data, this is what the flow looks like. So it will call global platform core APIs, then the syscall and opticore handles that and routes the traffic, and it will further performs a couple of function calls where it encrypts the actual data using a couple of keys involved. I'll talk about the keys in the next slide. And finally, once the data leaves TE, they're encrypted. So without key, it's no use. So once it reaches TE supplicant, then TE supplicant will place that file in the corresponding file system based on the configuration. This is what the flow looks like. So hardware unique. So this is very important because this is a master key that's stored separately in the place called OTP, one-time programmable fuse. So this is what's used to encrypt the whole disk or whole. This is what provides full disk encryption. So this is what provides a protection against offline attacks. So if the keys that are encrypted using uh, hardware unique key in this particular device can be decrypted only in the device. So it cannot be taken out and cannot be decrypted anywhere else. So that's the protection it provides. It serves as a root of trust. So this is not used for encrypting the bulk data. This is used only to derive multiple set of keys for security reasons. It's just 128-bit symmetric key. As you can see here, this is how this key is used to derive multiple other set of keys. The secure storage key, the second key, as you can see on the left side block diagram, it basically is generated by applying HMAC on hardware unique key plus static string. So once it's generated, it's never saved onto the disk. It's just stored in the memory when Opti is booting. Then it further is used to generate trusted application storage key, which is a per trusted application storage key. So each trusted application will get to have its own key. So this key is what's used to encrypt or decrypt the file encryption key. So the file encryption key at the end is what's to encrypt the actual block of data. So the file encryption key stays encrypted onto the file system. So as you can see on the right side block diagram, so the encrypted FE encrypted file encryption key, is decrypted by supplying trust application key. Then once it's decrypted, then you take the plain decrypted file encryption key, then you take the block data, like actual block data file, then you use AES-GCM to perform the decryption or encryption. So here it uses AES-GCM, so which is authenticated encryption with associated data. So by default, it provides integrity protection. So this is the flow. This is the flow. This is what the flow looks like to encrypt or decrypt the actual block of data in the OT. All right. Secure storage misconfiguration. So the hardware unique key is like a master key. It's used to provide utmost security. So it means even if you take the full hard drive out and try to extract the data, you cannot do that without the key. You cannot even extract this hardware unique key from the OTP because it's got tamper resistant. So, but that's the ideal state. But if you don't configure this hardware unique key properly, then it's not going to be 100% use. For example, one of the misconfiguration could be this hardware unique key is just all zero. Sometimes whatever that comes with the firmware or whatever comes with the device will be used for the production grade devices. That way, like attacker will be able to find the static string easily by extracting from the source code, and he will know the all zero key because it's all zero. Then the attacker uses these two combinations to derive all the keys. Then ultimately he can even decrypt like anything you store in the optic secure storage. The second misconfiguration is hard-coded static. Sometimes the source code will have this key hard-coded. So if attacker gets the source code, they can just run a string command or just do the reverse engineer ring to get the static key. And the key leakage. So sometimes because of improper designs, applications will be exposing set of APIs. For example, trust application will be exposing set of APIs using which you can extract the key, using which you can extract the hardware key. So that's not how you should do secure design. So this APIs should not be able to extract the keys or leak the keys outside because Opti will have access to these OTP slots and it will need to have access to generate set of keys. So, but if your application exposes those APIs to leak the key, then that's not a proper design. Sometimes the other common misconfiguration is the same hardware unique key is used across like all the devices. So if one hardware unique key is compromised, you are putting all entire device fleet at risk. So below or the some of the best practices in implementing hardware unique key. So in ideal case, a key should be created from within the device using physically unclonable function. So that's what Apple does in the uses secure enclave in Apple devices. So during manufacturing line, so upon first time running, so it is checking for the keys presence. If not, it will call those function. Then the function will use cryptographic accelerators to generate the key and stores the key in the designated location. So that's what the internal firmware should do. It means the key is never exposed outside and the key never leaves the SOC system on chip. But sometimes some formats don't have the capability to do that. So if that's the case, you can generate the key, but this is still not recommended. You can generate the key outside and put it in the storage like OTP or any other secure storage where your OT has access to. If that's the case, the environment or the workstation that's doing this should be tightly controlled. So in the manufacturing line, you should have proper access for authentication. It should have proper protections and security controls. Also, the transfer that you are doing, it should be a serial communication. It should be made securely. You need to make sure there are no man in the middle or no malicious application listening on both ends to extract the key. And you should follow secure provisioning process. Sometimes some MPUs manufacturers provide this process. You make sure where you make sure you authenticate the device. Um, before putting the key in, so to prevent the key extraction. It basically leads to another supply chain problem, so you need to authenticate the device before you putting the key inside. You need to trust that, otherwise wrong malicious device will get the key. And once the keys are provisioned, the workstation should remove all the traces. It should flush out all the key traces that exist in the memory. Also, it should not save those keys data in the on the disk, and it should also have like proper auditing, monitoring solution. That way, like we can audit these keys if the keys to make sure the key is not compromised. Um, Having said that, though, your MPUs should have support for key revocation. So if your key is compromised, it needs to have a capability to rotate the keys, ignore the old one. All right, finally, we have reached our final slide. Um, So I'll talk about challenges in enforcing strong controls in medical devices. The first and foremost challenge is detection and monitoring is almost impossible in some devices because since these devices are very old or it cannot be connected out to the internet. So it cannot be connected out to your backend server. So because of hospital restrictions or because of device lack of device capability, so it doesn't have that connection, so you cannot do real-time monitoring or detection or response on those devices. So even if your device is compromised, it will take like months to react to that incident. And the other problem is sometimes these devices run on very low computing power, so it doesn't have proper resources. But thanks to cryptographic accelerators, this problem is slowly going away, but still exists in old devices. And connectivity, as I said earlier, doesn't have like connection, network connection, so it's also very hard for you to push the software patches, security patches, even if you find some vulnerabilities. And some devices are decades here old, so security was not a thing when they were building the system. So introducing security now will create a lot of like financial and logistic problems. And again, safety versus security trade-off. So you need to prioritize safety or security because it's a patient's life and it's taking a huge impact on that rather than security. And some devices, because of lack of connectivity or doesn't because of lack of update remote update capability, it needs to be updated manually. So it creates a delay in issuing security patches and lack of shift left approach. So some devices they just apply security on top of it, just see security as a checklist instead of following shift left approach. So they need to integrate security in their software development lifecycle by doing proper design and threat modeling to reduce the attack surface. All right, that's it. Thank you for listening to my presentation. Bye bye.